So there is a lot to summarize, so let's start. And the idea today is to conclude the ON nonlinear sigma model and hopefully start some large N analysis, so that the tutorials are tomorrow and after tomorrow, right? Very good, so that then you'll be ready by the tutorials. We will already do some large N analysis at the level of this model here. Can you hear me okay? Is the microphone loud enough? Yeah? Okay, so the goal was, what we set up to do was to study the ON nonlinear sigma model, which is a model where we have a vector n that is in a sphere. We can either just keep in our mind that n needs to be in a sphere, or we can put a Lagrange multiplier and force it to be in the sphere. It's the same thing. And we want to study this quantum field theory. Now, if you zoom in close to the North Pole, why do I say that? Because if this vector pi is small, that's what I'm doing, right? N is approximately equal 1 plus quadratic and then linear in the other direction. So that means I'm considering some kind of tangent to the North Pole. I'm assuming some expansion. This would be good if expanding around the North Pole would be good. And if I do it, then we get this. We get n minus 1 massless fields. Here I rescaled pi to put the coefficient 1/2. Then the coupling, like we discussed in the beginning of the lecture yesterday, would appear on the vertices. The higher the vertex, the higher the power of the coupling. And we get an infinite set of interactions, and that would be one way of describing this theory. And if we were powerful enough, we would have to do Feynman diagrams using all these infinite vertices. Okay. Then, at that point we stopped and said, let's do some normalization group analysis. Let's see how this theory wants to behave at low energy. If we start assuming that I have this theory, and it comes endowed with some natural cutoff, right? I'm doing an experiment. This n is like a spin, so I go up to some cutoff, lambda. But then I want to zoom out. I want to consider lower energy, so lambda is too small of a cutoff. I don't mind going to a bigger cutoff, right? Because the experiments that we do are still at distances much larger than that cutoff. So let's decrease the cutoff. Why keep track of everything if all we care is low energy? So we started integrating out. We decomposed the field into fast modes and slow modes. This phi was the fast modes. We plugged it into the Lagrangian. We got some effective action. That was the original action for the slow mode, plus the some quadratic action for the fast fields phi. And because it was quadratic, we just integrate out. We just expand. We do the weak contractions, we integrate out the quadratic field, and at the end of the day, after integrating out the fast fields, what do we get? We get the original action again, the same action, right? For the field, okay, we called it n0, but now I'm relabeling it as n. So for this field that I care about at low energy, n, I get the same action, except that the coupling got shifted. And what was before 1/2 is 0 square, now I got this extra shift. And so this square bracket would be what we call the renormalized coupling. It's the new effective coupling. It got shifted by this amount, n minus 2 times log of the ratio of the cutoffs. That, I remind you, was from integrating out. It came from integrating out, doing this tadpole-like diagram, where we did this, integrate out this massless particle between some momentum, and this gives some logarithms. And that's what we got. Now, let me emphasize what this means. This means that if you are experimentalist A, you have a very good lab. Your lab can resolve up to some very, very big cutoff, that is very, very small distance. You have another experimentalist A tilde, whose lab is not as good. That experimentalist can only resolve up to some cutoff lambda tilde that is smaller. That is up to in momentum, so bigger in distance, right? And the statement is that, however, you both agree, if you do experiments, like, for example, a correlation function of two operators, one at position x1, one at position x2, for A is the same as for A prime if, of course, the distance between the 2 points, x1 minus x2, in this case, is much bigger than 1/, both cutoffs, the cutoff for A or 1/, the cutoff for A prime, right? Provided we are asking questions that are way below the cutoff, both agree. All good? That's what normalization means. Okay, so this equation for the effective coupling, I can code it into a differential equation. That would be the main result of last lecture, which tells me that the beta function for the coupling of the ON nonlinear sigma model is n minus 2 over 2 pi times the coupling to the 4 with a very important minus sign. Okay? This very important minus sign tells me that if I plot the beta function as a function of the coupling square, say, then here I start negative, then I don't know. But here in the beginning I trust, right? We are doing an expansion, higher and higher terms will give higher powers of E0. And so you see that if you are at some small value of the coupling, and then you evolve under the RG, you integrate in the RG, right? Then the derivative is negative and you are at small value, so you go back. Because the derivative is negative, right? And so at high energy, we conclude that at high energy, this coupling effectively goes to 0. If I hold it fixed at some finite energy, and I trace it back to high energy, at high energy the coupling would go to 0. And that would mean that in the UV, we have n minus 1 massless modes. In other words, in the UV, the coupling is very small. I can drop all these terms, and I keep n minus 1 massless fields. Right? In other words, in the UV, it's fine to expand around the North Pole. Let me make a comment that expanding around the North Pole is breaking the symmetry. We had a sphere, all points were equal, and now we are kind of saying that at very high energy, we spontaneously break that symmetry. That's true. Right? Indeed, then we get n minus 1 modes, and you can think of them as that expansion. One last comment. You see that what happened here was that you had some configuration of some vector n, and now that configuration is weighted with a new coupling. Right? So you see that what is happening is that as you go to low energy, the coupling is increasing. The coupling decreases as you go to low energy, right? To high energy. So it increases as I go to low energy. So as I'm integrating stuff out, the coupling is increasing. Right? So again, integrating out past modes led to E0 increasing. Correct? Now, if you get this E0 increasing, it would be equivalent. You could, from the point of view of the action, it would be increasing, it would be equivalent to decreasing the magnitude of the vector n, right? If you think that from the point of view of the action, instead of increasing, sorry. No, E0 increases would be increasing the magnitude of n. Sorry. Increasing. Sorry, now I'm confused. So we integrate out fast mode. And so this is negative, so this quantity decreases, so the inverse increases. Yeah, so E0 increases. E0 increases, so E0 increasing, I would reach the same thing if n decreases. Ah, it was okay. Oof. Okay, I was worried. Okay. Okay, remove the slash. No slash. Okay. I was worried. Because that's what makes sense, because you see, what's happening is the following. You have a vector that was a unit vector, right? But we are averaging because we are integrating out some fast modes. Right? So imagine that you have some vector and you average it. And if you average, if you zoom out and you average, like it looks like an effectively smaller vector, right? Because you integrate out. So now this leads, upon average, to a smaller vector. And so that would match our intuition of integrating these guys up. Okay, great. And one last comment that we made yesterday was that when n equals to 2, there's no flow because the theory is effectively free. Now, what happens then at low energy? At low energy, the theory becomes strongly coupled, the coupling becomes big, and it's much harder to ask what is happening at strong coupling. Is a much more challenging question. And you would have to work harder to understand that what happens is that the particles are not massless, but they gain some mass. So the idea is that at low energy, these particles develop some mass m.
Pedro?
Yes.
Before starting this, can I ask a question about?
Yeah.
In RG, normally we after we integrate out fast mode, we scale energy to go to the first cutoff, right? We rescale it. Normally we do this, but here we didn't do that. Is it clear what I'm saying? There is two steps in normal RG.
Again, now it depends how you want to think. Yeah, I feel like it's the same as with conformal transformations. So I'm trying to explain a way that I think is self-consistent, but each person can think in its own way. For example, I can decide that for me, I'm changing the cutoff. You can decide, no, the cutoff is like my lattice unit. So I want my lattice unit to be 1, right? So I want to measure things that whatever experimentally says the cutoff, the minimum distance, I want to call that 1, right? Then at the end of the day, you lambda and lambda tilde, you want to call them both 1, right? You want to say the cutoff is the same for both because it's a question. And then you have to rescale to compare quantities. That's not what I'm doing. I'm saying I have some cutoff. Now I'll have a new cutoff in the other theory, which is, and the ratio of this cutoff over this cutoff is something physical, right? It's how much it requires money to go from this to this, right? To have a better lab and to have a better cutoff, right? So this over this is, if it's 100, you have 100 times better lab, something. But it really is up to you. What's important is to focus on physical questions, on some physical quantities. So here is an example of a sharp physical equation. If you can phrase your question in terms of something that is confusing you in some equation, it will be better. Otherwise, it's true, you can rescale things. You can decide to keep whatever you want fixed. It's units. So units, all that matters is dimensionless quantities, ratios of things. So whether you decide that your cutoff is 1 or not, it doesn't matter. What matters is when you have some physical quantity. So yeah, if you have some confusion about a particular equation, ask me, or ask me at the end. Okay, so the claim is that at low energy, we have not n-1, but n particles with mass m. Now, we are going to find some evidence for this claim in a second. But let's try to ask ourselves right now, what would be m? What would be this mass m for these particles here? Now, you see that m if you are experimentalist A, you would say, I have my theory, I have a coupling that is dimensionless, so I could have a function of that dimensionless quantity, right? And I have, the only units I have is my cutoff, lambda, right? And so the result must be cutoff times f of E0, right? Just by dimensional analysis. Now, of course, experimentalist A prime would say, no, my cutoff is lambda tilde, and I have my function of E0 tilde. Now, of course, both are right. A mass, is whatever they measure, but it cannot depend on the precise experimentalist, right? It cannot depend on who is measuring this mass. And so this mass, if I take really the derivative with respect to the cutoff of this lambda tilde f of E0, let me write like this. Should be equal to 0, but this is equal, or let me take derivative with respect to logarithm of lambda tilde. But this is equal if I take a derivative to lambda tilde times f plus the beta function times f prime, derivative times, with the lambda outside. And this gives you a simple differential equation, right? This gives us, this is a simple ODE, the fact that this stuff is 0. Let me write a solution right away, right? You just plug beta, you solve this differential equation. And this solution to this simple differential equation would be that f is proportional to e to the minus 2 pi over n minus 2 E0 squared. If you plug it there, you see that the derivative would cancel the beta function and give back f. And therefore, if such mass exists, you conclude that the mass should be something like some number times the cutoff, should be approximately equal a number cutoff e to the minus 2 pi over n minus 2 E0 squared. The fact that you started with a coupling that was dimensionless and you generated a mass, this is what is called, generation of this mass is what is called dynamical mass transmutation. And as I said in the last lecture, it's basically the same that you would say for pure Yang-Mills theory. You start with a theory which is just Yang-Mills, you have just a dimensionless coupling, and then you quantum mechanically, non-perturbatively generate glue balls that are bunches of glue that are dynamically generated. And so here it will be the strongly coupled dynamics of this theory that you would start with what looks like n minus 1 massless fields, and then you will end up with some fields that are not massless, but they have some very small mass. You see that if this coupling is very small, this quantity is very big, and so this mass will be very small if E0 is small. Now, before I want to conclude this part of the topic, this part of the lecture, with a statement that I'm not going to derive, but I'm happy at the very end of the lecture, if you want, we could go over together. It's explained in great detail in the book by Polyakov. So I want to just write a sharp equation. Suppose I define some, I'm an experimentalist like A or A prime, and I define some coupling that I want to say depends on momentum P. P is some energy scale. Now, how do I do it? Right? Because people say, I just have a coupling at energy, whatever. But what exactly do we mean? It needs to be some physical observable. So let's say we compute the correlation function, some amplitude, at equal momentum, at 4 equal momentum P. So I define it as I have some amplitude, some correlation function, some object where all the momenta are the same. P, 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 and P. Right? If you want P minus P, P minus P. Right? So that's the definition of this quantity.
The coupling is some correlation function.
Right. So we define it as the value of the correlation function at energy P. Right? If I want to say some quartic coupling, you see the cubic coupling is 0. The 2-point function would be normalized to 1. So the 4-point function would be the first one that would be interesting for us. So we say the 4-point function at some energy P is my definition of coupling at energy P. Right? It tells us how 4 probes interact with each other at energy P.
So, but this is the same coupling that goes in the Lagrangian?
No, no. This is defined like this. Right? So here what we are doing is we are defining some new object which is some coupling at some energy scale P. Defined by your favorite quantity. It could be that correlation function that I wrote there, but instead of 2 points, you put 4 points and you do it in momentum space. P, 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 P. Anything. Some representative object like that. Okay. So now you would say, well, okay, this quantity is actually some function of what? If I'm at energy P, it could depend on P measured in units of my cutoff. That's dimensionless. That's fine, it could be. And it could depend on my coupling is 0 square. And now you do a bunch of shenanigans, a bunch of arguments similar to the one that I did there to derive the mass about, well, but it should not really depend on cutoff, etc., etc. And now I'm going to jump this. And this, as I said, it's just some simple but important RG arguments. But I want to that you can find, as I said, in the book by Polyakov. But what's important is the claim that this definition plus now the knowledge of the beta function would lead to the following result, that this E0 square of P is equal to E0 square of mu divided by 1 plus n minus 2 over 2 pi E0 square of mu times log of P square over mu square, where mu is some energy. And so E square of mu is equal to 1 experiment. So I want to stress that this result has no cutoff anymore. Right? You do the experiment once at your favorite energy, mu, that's E square of mu. And what the renormalization group told you is how do I move in energies and how do I learn from that result of that experiment at some energy mu, what's the result at my new energy twice mu, or 3 times mu, or 4 times mu. Right? And so it definitely deserves a box. It's a very powerful equation. This would be true and well justified provided this coupling stays small. All these couplings stay small. As the couplings go big, then you would lose control. So this would be okay for small coupling before it becomes too big, such that this term here, for example, should be small compared to 1. Okay. Now, let's try to consider this model in a limit where we can actually make some analytic progress.
If we had to do, say, for a slightly larger coupling, the same analysis could go through. Only thing we would have to do is calculate the beta function for slightly better approximation, right? Like beta function we calculated when we expanded our fields to only till, say, quarter.
Yeah.
If we could calculate that for higher orders there, then this would work for higher couplings, bigger couplings.
Maybe a little bit bigger, but very soon, if you are running into trouble, yeah, I would be skeptical that you could do much better than this, because eventually all terms will start mattering. Yeah, maybe, of course, you could probably improve it a little bit, but I don't know, for example, personally, I would not know how to do it in a simple way. I'm sure it's possible. I never thought much of it. So now, let's consider what is called a very important limit, which is the large n limit. What's the large n limit? Is the limit when n is large. We have n. If n is large, we call it the large n limit. And so let's study this model where n, our model, when n is going to infinity. And so what do we have? We have our integral over our field n over our Lagrange multiplier lambda e to the minus 1 over 2 E0 square integral d to x. And then we have del n square plus lambda times n square minus 1. This will be, say, our partition function. Now, notice that, again, this lambda is a field, right? It's not a number, it's a field. For each value x1, x2, there is a lambda. Now, actually, you see that n appears quadratically here. Right? N with this Lagrange multiplier appears quadratically. So it is tempting to integrate n out. Now, normally we wouldn't do it, because if you integrate n out, you will generate a very complicated action for lambda. Right? But let's see what we get now. So what we do now is we integrate the n scalars, n1 up to nn out. So what do we get when we integrate this n squared plus lambda n squared? What do you get when you integrate out this, when you do this Gaussian integral? You did it in QFT, right? You integrate, you did when you had d phi squared. Let me go to notation where you are more familiar. You would have d phi squared. This lambda you would call m squared. And then you have phi squared, right? That's the notation we normally use, right? Phi squared, m squared. Then what do you get when you integrate out phi?
can go to Fourier space and
You can go to Fourier space, that's good, and then
multiplication of propagators.
that would
1 over propagator. 1 over P2 plus M, right?
almost correct. In other words, what is that product computing effectively that you are thinking about?
I think phi K2 plus M product over all Ks, right?
That's right. So a product, when do we compute a product of things? A product of eigenvalues of a matrix is the determinant, right? So we integrate a quadratic form. It's determinant of that quadratic form. In other words, let's write it. There is integral d lambda. Let's write the action that doesn't depend on n. Let's keep it here. E to the minus 1 over 2 E0 square. That minus cancels with this minus, so plus integral d to x of lambda. So this part stayed the same, just for this lambda here, right? But then we integrated out n, and n gives, when you integrate out a Gaussian, you get a determinant, right? More precisely, you get really determinant, or almost square root.
Square root of the determinant.
Square root of determinant. And so we are going to write in the exponent. So if it's in the exponent, we should put logarithm of the determinant of this operator minus box plus lambda. Square root, so 1/2. And what else should I put here, up here? Should I put 1? N, because we integrate out n fields, right? Each gives a determinant of n. And this n is crucial, because now you see that because n is here, if n is large, we can use saddle point. Right? If n is large, the action is very, very big. It will be dominated by whatever configuration minimizes that action. Let's recast this, simplify this a little bit. Log of determinant is the same as trace of log. And then the saddle point equations are just the variation with respect to lambda of the effective action that we just wrote for lambda equal to 0. Would give us what if we take the derivative? So the derivative of this first term would give 1 over 2 E0 square. And the derivative of trace of log would be, so this plus n over 2 is n over 2. Well, derivative of log is 1 over lambda minus box. That's the derivative of log. And we would have a trace here. And as you pointed out, what's your name, sorry?
Ami.
Ami? As Ami pointed out, a very good way of dealing with this object is going to Fourier, where this trace is nothing but the integral d to p over 2 pi square 1 over p square plus lambda. This is equal to 0. And therefore, we would conclude that we would get some equation for our lambda that would be 1 over 2 E0 square plus n over 2 integral d2p over 2 pi square 1 over p square plus lambda equal to 0. Now, this quantity here is what? This quantity, again, if I go to radial variables, is 1 over 2 pi integral d, let me call it r, dr, 1 over, or r here, 1 over r squared plus lambda. You agree? And now this integral, we should integrate from 0 up to some cutoff lambda. And therefore, this object is, well, this integral is trivial to do, right? So it is yeah, put a 2. I can put an extra 1/2 here. Then this is logarithm of this quantity down here, right? And therefore, at the upper cutoff, lambda square is very big, so I get log of lambda square. At the lower cutoff, r is 0 divided by lambda. And so that's what this integral would give. And therefore, we conclude that lambda is given by, at a saddle point, lambda is given by the solution to the equation. Let's write it. 1 over 2 is 0 square plus n over 8 pi logarithm of lambda square over lambda equal to 0. In other words, let me write lambda is equal to lambda square exponential of minus 4 pi over n E0 square. You agree?
Are we dropping the 1 inside the log? Should it be 1 plus lambda squared over lambda?
It should be lambda squared plus small lambda over lambda. We are ignoring that lambda because capital lambda is very big.
Right.
Yeah, so you agree?
Yeah, we're ignoring the extra term.
Ah, okay, so yeah. I understand what you say, yeah. Yeah. That's equivalent, yeah. So this is correct. And therefore we get this, and so this is the value lambda. Let's put some lambda star. Okay. Now let's zoom out a bit from the algebra and say, what does it mean? So the conclusion is that at large n, the Lagrange multiplier field, lambda, is equal to, if you want, some expectation value of lambda plus 0, where this 0 is fluctuations that are suppressed by the fact that n goes to infinity, and this expectation value of lambda is nothing but this lambda star. And so what happens that at large n, there is this effective action, right, that will localize lambda at that fixed value. Yeah.
Could we also have seen this by taking the dynamical mass transmutation and seeing that in action lambda kind of looks like a mass, and then.
Oh, but don't jump there. I'm going to do it. Yeah. Sorry, 1 second. Yeah, you're jumping to the nice punchline. Good. Yeah, I think you saw it already. But what we are this is what we are concluding. Now let's see what's the physical implication of this. Right now, as what's your name?
Charlie.
As Charlie is pointing out, then it means that if I go back to my action, I can think that that lambda there is not moving much. It's fixed to that constant. But as we said before, that if I put that lambda to a constant, I should call it m squared. If I have a quadratic field, what multiplies the n squared is the mass squared. Right? So we conclude that at large n, our action is approximately equal to derivative of n squared plus some effective mass squared times n squared, where m is basically square root of this lambda star, which is therefore e to the minus 2 pi over n is 0 square times the cutoff lambda. Right? And so we conclude what? That at large n, we have n massive fields with m given by this expression. And that, you see, beautifully matches what we had there in the top box when n is large. Then you can drop the -2, right? And that's exactly what we have there, derived through this more general RG flow argument. Right? And so this picture is, of course, at large n, where we can do all this. But now that we understand this, we say qualitatively it should be similar. If n is not infinite but 6, okay, lambda might fluctuate a little bit. It's not going to be really, really constant. But still, the fields will acquire some mass, right? There will be still n fields with that mass. And what could that mass be? Well, then we can go through that argument. Right? And everything now you see is consistent. So we start to have really this coherent picture. Yeah, Manu?
Starting with that equation, I think the sign of exponential is wrong there. Because when you take the 1/2e already.
I was so careful with all signs and so on, and yet I failed. Shame on me. Why did I fail? Derivative of log is correct. You said this sign is wrong? That's very sad news. Yeah, let's see. Help me. It shouldn't. It's definitely correct, right? We don't want an exponentially large mass. Where did I get it wrong then? You are zooming out. It's easier for you to see, probably.
Wait, is the Gaussian integral of the quadratic is 1 over square?
Ah, good. Yeah, the Gaussian integral, let me confirm. Let's do this carefully. Integral dx e to the minus alpha x squared. I rescale x by 1 over square root of alpha is 1 over square root of alpha, right? Okay, so determinant has negative sign. And good point, thank you. There is a minus, and there is a minus, and then this equation is good. Right? Very good. The Gaussian integral gives 1 over square root of determinant. Okay, so let's see what's the total picture then now. What's our final picture for this behavior of this field? And let's see how it fits nicely with our physical intuition. What happened? I hide it. So we started. So the punchline is for the physical behavior of the ON model is the following. In the UV, we have n minus 1 massless scalars that flow, acquire some mass, and flow in the infrared, well, if you want, to a gap theory. In other words, from a CFT point of view, you would say it's empty, right? Because everyone has mass. And along the flow, what we have is n massive, of course, very light, particles with ON symmetry. Right? And particles which carry an index of ON symmetry, a vector index of ON symmetry. And so what is happening is that here, all the way, except at the UV, symmetry is restored. While here, you would say, only in the UV, symmetry is broken. What we are doing is saying that in the UV, we pick some direction of the sphere to expand around. Now, which direction you pick? Any direction is good, right? So whenever you break a symmetry, it costs no energy to shift to another vacuum, right? And that is always associated with the existence of Goldstone particles of zero mass, right? Because you could put here or here or here or here. And what's the dimension of the tangent space? N minus 1. And so here the symmetry is broken, and we expect, therefore, N minus 1 Goldstone bosons. Let me put in quotation marks, because what we see is right away, if we are not in the UV, they don't exist. Right? Why not? Why can't I just break the symmetry and declare that symmetry is broken, and then I have some fluctuations around that broken symmetry? And the answer is that in 2 dimensions, continuous symmetries cannot be broken. Right? And that's the unknown theorem, and let me remind you. Okay? So it has to be like this. Okay? So symmetry could not remain broken. This could not have happened. So we knew that we had to restore symmetry, and so this picture had to be correct. And this is a consequence, let me remind you, of what's called the Mermin-Wagner theorem. This theorem tells us that you cannot have long-range order in 2 dimensions. So the following in 2 dimensions cannot happen. You cannot have a piece of material of this ON magnet where all spins are pointing in some favorite direction. And then outside, they are pointing in some other direction. So this would be order. This would be a material that is ordered. Here there is some order, and here there is another order, another phase. And so the claim is that this does not happen in D equals 2. Okay? Let me remind you why not. Let's see if this could happen in D equals 2. So in D equals 2, now let's think from a statistical mechanics point of view, right? So suppose we want to ask if these configurations could dominate the partition function and could be relevant in the partition function. So in the partition function, such you would sum e to the minus beta e. In other words, you would, by sum over all states, you would, if you group into bands, you sum with some number of states in some energy band e to the minus beta e. If you sum band by band, right? If you group in bins, you group energy in bins. Now, how does the number of such configurations grow? If I call the length of this curve L, right? If this length here is L, then this number of configurations would be some exponent to the power L, right? Imagine it's some random walk, right, of length L. At each option, I choose 3 options, right? That would give me 4 to the L. That's a big number. Of course, this is not a random walk because it needs to close. But it's it's still not 4 to the L, but it's a smaller number to the L. But it's some exponential of L. There are many, many options for this path. Do you agree? And so this would give me exponential of L times some number. So it would be linear in L. Now, what about the energy cost? What about the energy cost? Now, if this was a discrete symmetry, where this is spin up and this is spin down, what's the energy cost? Well, there is an energy, there is no energy here, there is no energy outside, but there is an energy at the transition, right? Because at the transition, you are not in the vacuum. You have up here and you have down here. Well, I'm not sure this is down. And so there is an energy, 1 unit here, 1 unit here, 1 unit here, all the way across the boundary. So the energy cost, as far as the energy goes, if it was discrete, it would also be proportional to L, right? You would have some energy per length at the boundary. Now it is, but it's not. It's not discrete. So we have to estimate how much energy does it cost to transition some vector here to some vector there. Right? So now you can see that what you can do is you have this vector n and you want to transition to some other direction. Right? But now you can change smoothly the vector. So you are not going to change right away. You are going to change it smoothly. Right? And we can do it over some band here. We don't need to do it abruptly. We can do it quickly. We can do it over some band here. And so here you would have, this could be of order L as well. It could be some finite width, right? And so, but the point is, how much energy does it cost to change the vector just a little bit here? Right? And you can easily see that if you want to change the vector by this, that del n squared, that derivative square, it only changes by 1 over L when you change the vector a little bit. That's how much the vector changes when you change the vector a little bit, that size of that small vector. And because the energy is the square of this, it's 1 over L squared. And so the cost of all this transition, all this cost is 1 over L happening here. This is the cost of what's happening here. Right? We are looking across this section here. Right? And this happens everywhere. Right? And so the total is all this times L. Right? So let me move up so that all of you can see. So again, the argument is each bit of change here is 1 over L squared. Each bit But then there are L of them, so in total 1 over L. And this can happen anywhere, so times L. So 1 over L squared times L is order 1. Right? And so this is order 1. And so it always loses compared to entropy. And therefore, these configurations never show up. And therefore, you cannot have order. Order is always broken. Entropy always wins, and it prefers to break order completely. Another way of seeing, that's the original way these theorems are stated, right? So this is order 1, and that implies that entropy always wins. And therefore, we have no order. Right? Order means breaking symmetry, right? You pick some vector in some direction. And so another way of seeing this is that if you went to these free massless scalars, then you could ask, my free massless scalars are these vectors that are massless, that give me the fluctuations around the North Pole. Right? We start at the North Pole. We say our vector is pointing here, and far away it's also pointing here. And I want to ask, do the vectors stay pointed in the same direction? We know they don't. We just proved it. But we want to ask, do they? So what would be a measure to saying how close are they to pointing up? It's a measure of the fluctuations of this pi, because pi is the deviation from pointing up. And if you have a massless field in 2 dimensions, the propagator of a massless field grows with distance. The propagator of pi with pi, these massless fields, grows with logarithm of the distance. Right? Just the propagation of a massless field in 2 dimensions is logarithm of x. And so these fluctuations increase with distance, breaking the order. Right? So they don't. This is different from higher dimensions where the propagator would decay, and therefore you could form order. And indeed, if you did this analysis in higher dimension you can and you do have symmetry breaking.
Sorry, I think I missed it. Why is it? How do we know that it's log? Where do we see that?
It's just a propagator of a massless field in 2 dimensions. Right?
Oh, 2D.
In other words, it's going back to position space 1 over p squared. Fourier transform of 1 over p squared in 2 dimensions gives log. Is it okay? And and this would be the Mermin-Wagner theorem. Anyway, the punchline of all of this is that you see you have a very non-trivial theory that started its life conformal. At high energy, the particles, they would like to be Goldstones. We would like to have these massless particles because we would like to say our model has some energy that doesn't, if you pick a constant vector n, that minimizes the energy. And we could pick it here or here or here. And so we would say symmetry is going to be broken, and then there's going to be a massless field for fluctuations around it. That would be our classical intuition. That classical intuition is wrong, because quantum mechanically in 2 dimensions, the correlations grow. And what we know is that symmetry is not broken. Instead, symmetry is restored. And you have particles. They are not massless. They are very light. It's true. They are exponentially light. But there are n particles, not n minus 1. And they are massive, and they restore the ON symmetry. So that in total, there's no symmetry break. And so the conclusion is that we have an interesting beta function. This model is not a CFT at the quantum level. But instead, it has all this rich behavior, all this rich physics that we explored in these lectures, including dynamical mass transmutation and so on and so forth. So let me conclude. And by just reminding you, as I said in the beginning, that this type of theory shares many things in common with, as I said, Yang-Mills theory in 4 dimensions. What would we write in that case? We would say there is some coupling, 1 over g squared, integral. Now we are in 4 dimensions, d for x times trace of f squared. We have some non-abelian gauge theory. Right? And we could do the same. We could write the fast modes, the slow modes, etc. and compute this is the coupling. And if we were to compute the beta function for this coupling, we would get the famous minus 11 over 3 times n times this coupling cube divided by some 16 pi square. Where this beta function is the derivative of the coupling with respect to logarithm of lambda. And again, this minus sign is the same minus sign that we saw. This minus sign is what gave rise to the Nobel Prize of 2004 to Pulitzer, Gross, and Wilczek, and this is asymptotic freedom. And again, and here, what we expect is that there exists in nature glue balls, which, if this is a gluon, pictorially you can think it's just really a ball of gluons interacting, and they have some mass m, and this mass m would be dynamically generated. Now, how do we go about computing this mass of these glue balls, etc.? We don't know. We don't have a good approximation scheme to compute this mass except using computers. If you ask how many glue balls are there, we know. How do we know? It's on Wikipedia. There are 3, I think. But without Wikipedia, we would not know. And people that made Wikipedia, they use computers to simulate the theory and see that indeed you find 3 stable particles below threshold. And of course, we could try even developing a large N approximation to studying QCD is an open problem. There are many things we can do at large N, but there's even just trying to study this theory in the limit of a large number of colors is still an open problem, where N would be the size of these matrices here. So a key difference compared for this theory compared to this theory is, of course, one is in 4 dimensions, one is in 2 dimensions. Here, we are dealing with matrices. Our fields are matrices. This is what a non-abelian gauge theory is. It's because these fields are matrices and they don't commute. Whereas our fields that we started with here were vectors. And large N limits of vector theories are very easy. And we did it in 5 minutes. Large N limits of matrix theories is much harder. It's an open problem, basically, how to efficiently take large N limits of matrix field theories. And starting to understand what could be the tools for dealing with large N matrices is what we are going to do tomorrow. And then in the next 2 tutorials. Okay. Thank you.